So hello guys, welcome back to practice channel of Geeks for Geeks. My name is Dhananjay Mishra and today in this live session we are about to discuss a problem statement which was recently asked in Morgan Stanley. So before further starting this, let me first of all clear and ensure that whether my voice and whether my video is perfectly audible and visible to you or not. So please acknowledge that if it happens. So guys, it will be great if you can acknowledge that whether am I audible or not. So okay, let's begin. Let's begin with today's session. So guys, as we discussed that this problem was recently asked in Morgan Stanley, and let us now begin with the problem statement. So the problem statement reads, and the name of the problem statement is row with maximum number of ones. So let us now read the problem statement. We are given a Boolean 2D array of n cross m dimensions where each row is sorted. Find the zero-based index of the first row that has the maximum number of ones. So the question says that we are given a Boolean 2D array. The Boolean 2D array means that each value in each cell of the 2D array will be either 0 or 1. In other terms, we can say that we are given a 2D binary array. Binary means we only have two values, that is either 0 or 1. So we can say that we are given a Boolean array or a binary 2D array. The dimension of this array is n cross m. So n depicts for the number of rows and m depicts for the number of columns in that particular 2D array. And furthermore, we are given a stat or a help that each row is sorted. So basically, each row in this 2D array is sorted. So our task is to find out the zero-based index of the first row that has the maximum number of ones. That means while doing traversals, we have to find that row which is having the maximum number of ones among all the possible rows. And one more thing here, we have to notice that we have to return that first row which is having the maximum number of ones. So to further elucidate this case, if I say that if I am having more than two rows having same number of ones, then I have to return that row which is having lesser index. And furthermore, we have to consider the zero-based indexing. So let us now further to understand this problem statement clearer, let us look at the sample test case. In the first sample test case, we are given the dimensions of a matrix of 4 by 4, that is n is equal to 4 having 4 rows and m is equal to 4 having 4 columns. Now the array elements are, or the array we can see is a Boolean array where each value is either 0 or 1, or we can say that instead of Boolean the array is a binary array. So the output of this sample test case is 2, because as we can see that the third row is having maximum number of ones, but we have to return the zero based index. So therefore in the zero based index, this is the first row having zeroth index, the second row having 1 index, and the third row having 2 index. So therefore we return 2. I hope this sample test case is clear to you. So now, after reading the problem statement, the name of the problem statement, and understanding what the question demands and what is our task at the end of the day, that we have to return the row in the zero based index form having maximum number of ones. And if there are more than one rows having the same number of ones, we have to return the first row having the lesser index. So let us now jump on to the approaches that comes to our mind. So the first approach that comes to our mind is that we normally traverse each row and each column, and we will find the answer for each row, and we will take the maximum number of ones that is possible after having traversing each row. By saying that, I mean that if we start traversing from the first row, we will check at which index we are encountering or facing the first one, and we will store the index of that one, and as we know that each row is sorted, that means suppose if I am encountering first one here, so if each row is sorted, that means all the values on the right side of the first one we encountered will also be 1. Hence we can deduce the fact that if I'm getting my first one here, then the total number of ones will be the size of the column minus the index at which I am getting the first one. So for example, to get it more clearer, in this first row, we are getting first one at index number 1. So let me write down the first row here, that is 0, 1, 1 and 1. Let me do the zero based indexing, that is 0, 1, 2 and 3. And the size of the column is 4, that is m is equal to 4. So as I said earlier that we will store the index of the first one we encountered in each row. So in this case, we encountered first row in the 0th row is at one index, and to find, and we know that each row is sorted, so therefore all the values to right of this one or the first one we encountered will also be 1. So to find the total number of ones in this row, what we normally have to do is subtract this index from the total column or the size of the columns. So in this case m is 4, so we will subtract 4 minus 1, so the answer will be 3, because we can cross check that we are having 3 ones, 1, 2, 3. So this is how we will do the same approach and follow the same approach for each and every row, and we will update the value of the so after that we will take a variable count which will store our maximum number of ones till now, or so far we have acquired the maximum number of ones. So if I do iterations for this first approach, basically for this first row we are having count is equal to 3. Now in the second row we are having count is equal to 2, but this count is greater than the count having in the current row, so we will not update the value of count. Similarly, in the third row or the second row, if I consider the zero based indexing as asked in the question, we have 4 ones, right? So we will update the value of count by 4, and each time we update the value of count, we know that this can be a possible answer, so we will also update our final value of answer by that row. Now in the last row or the last iteration, we see that there are no ones, so therefore our answer will be 0, so we will not be updating count as well as answer. So after doing all the iterations or traversing all the possible rows, we will finally return the answer, that is the index having the maximum number of ones or the rows having the maximum number of ones. So after doing this approach, we can see that the time complexity of this approach will be n cross m, that is the dimension of the matrix, because in the worst case we will have to traverse each and every cell and each and every row, hence that gives us the time complexity of big O of n cross m. Talking about the space complexity now, the space complexity will be big O of 1, because we are not using any kind of array for some storage purpose or likewise that. So therefore the space complexity remains big O of 1. So as we can see or observe the fact that this time complexity is pretty much heavy or pretty much large to be implemented, but we can see that, or we can use the fact that if we observe it carefully, then we were given that each row is sorted. So whenever we encounter or we face some array or strings question in which the each and every element or attribute of that particular array or string is sorted, then the first thing comes to our mind is binary search. Binary search in the sense that if we have to find some value in a better time complexity than linear, that is in the logarithmic time, we can implement binary search and use binary search to find that particular value in logarithmic time. So we will use the fact of that row is sorted, and we will use binary search to find the first one in each and every row. So let us now dive in deeply to see how binary search will work in this case. So basically what we will do is that we will traverse each and every row. Traversing, I mean we will visit each and every row, but unlike in the previous approach, to find the first value we will be using binary search instead of doing linear search as we did in the previous approach. So well, suppose if I want to do iterations, I will first of all be at this row and I will use binary search to find the first one or the index of the first one that I'll be encountering or facing in this particular row. So if I do that, so the approach will be same as above or as the previous approach we followed, but the only change will be that instead of using linear search, we will be using binary search to find the first index or the first one in that particular row. So if I talk about the time complexity of this approach, so we are visiting each row, and at each row we are applying the binary search. So for each row, that is if we are having n rows, we are applying binary search to each and every row. That means here our search space mainly includes the m columns, right? Because if I'm at this row, I have to travel. If I'm at this row, then I have to check for all the possible values here. So all these possible values are the columns basically. So therefore, we have to search or apply binary search in the search space, which is number of columns. So a time complexity becomes n into log of m. Talking about the space complexity will as usual remain big O of 1, because the logic is simple that we are not using any extra space. Hence, the time complexity of this binary search approach is n log m, and space complexity will be big O of 1. Now, if I do the iterations, or to see that how binary search will be implemented is this in this, let us look at the few iterations to understand it more clearly. Now, I will discuss the steps which are involved in doing any binary search approach, or to implement binary search in any kind of question. There is a particular template and steps we have to follow. So in our previous videos also, we have discussed that to implement binary search, first of all, we have to find the search space in which our answer can lie. The second step, after finding search space, we have to shift our search space to left or right depending on the conditions. So if I want to elucidate this part, or if I want to extend this part, so this part contains 2 or 3 steps. So the first step is that we have to find the mid value and check whether this mid value found is our possible answer or not. If it is a possible answer, then we store the temporary answer, and now we can see that we have to found the, if I talk about this case, this particular case, how will we apply binary search in this particular case, then we can see that suppose if my mid is pointing to this value, let us suppose if my mid is pointing to this value, then we have to find the first one. So if my mid is pointing to this one, then there is a possibility or room for search space that we can still find a one on the left hand side. So therefore we will not stop here. Then we will store the temporary answer, and after that we will update our low value to, or we will update our high value to mid -1, and by doing this updation we will be moving in the left part. But if I compare or talk about the relation with the normal or the general binary search, if I want to search any particular element in a sorted array, then if I find a value equal to my target element, then we normally return, right? But in this case, we don't have to find a particular element. We have to find the first index having value 1. So if I encounter a 1, then there might be chances that there can be another one having lesser index than the current value of mid. So therefore, we can't stop at a particular temporary answer. So we have to shift our binary search, or we have to search our binary search or search space in the quest of getting a new value of 1 having lower index than the current value. So that's why we are using the term of temporary answer. In the case if my mid doesn't satisfy the condition, then I will shift my search space into the left side or the right side. So this is the second step, that shifting of search space to left or to the right side. So this is how, or these are the main steps we will use in the binary search. Now, after talking about this binary search, is there any room for doing much better, or doing something little bit extra, or just using our mind and logics to implement a new approach, or to go with a new approach which is having a way much better time complexity than n log m? So yeah, the answer is yes. we can implement another approach, or we can think of another approach that is having a way much better time complexity than n log m. So let us talk about this. So if I copy down my array again, so the 2D array was, so this was my 2D array which was given to me. So if I delete everything else, yeah. So this was my 2D array given to me, and we know that the fact that the 2D array is sorted. So we will start from this value. We have solved the approach earlier in a similar question in which we have to find the element in a 2D sorted matrix. So the same approach will be following here, and to understand this approach more clearly, you can watch out my previous live sessions in which we discussed the same problem statement in which we have to find an element in a 2D sorted matrix. So we will be using the similar approach, and I will be discussing you in this live session that approach again from the beginning. So basically we will be starting our pointer or our iteration from this value. So the row number for this value will be 0 and the column number will be m minus 1. So the basic approach we'll be using is that we will first of all compare whether this value is 1 or not, or this value is the final answer we want to find or not. That is, in this case we have to check whether this value is 1 or not. So we know that each and every row is sorted. So if this value is 1, so there is still room, or we can still go to the left side in the quest of finding a newer value of 1 which is having a lower index than this index. So if I do indexing, that is, if I take the first row and if I do indexing, then if I'm pointing initially at this, so there might be chances that there can be still more ones on the left hand side having lesser index than the current one. So I'll be moving or decrementing my column pointer by 1 by keeping the row pointer constant, that is as it is. So now here we are doing a step by step iteration to understand this approach, because this approach is quite dependable on the observations and the iterations we do. So we will try to understand this approach by doing step by step all the iterations. So now in the next iteration, my pointer is pointing here. That is, my row is still pointing to the 0th row, but my column is shifted one element to the left. So still here we are getting 1. There are still chances that we can still get another 1 on the left hand side. So we will again decrement our column pointer by 1 and we will reach here. Now still we don't know whether or a machine or computer doesn't know that there is still any 1 on the left hand side or not. So in the quest of finding another 1, we will be again shifting our column by 1. So our column by 1 value to the left. So we will be decrementing our column and we will reach in the next iteration here. So we will see that this value is not 0, right? And as the row is sorted, that means all the values to the left hand side, if there are any possible values on the left hand side of that index, they will obviously be, and it is guaranteed that they will be also 0 because the array row is sorted, right? So now after getting this, we will update our answer, because we will see that we have found this many number of maximum values, right? So we will move on to the next row because we haven't found this value here. So we will move to the next row by keeping our jth pointer as it is. That is, in the first row, whatever was our jth pointer pointing to, we will keep that pointer same, because basically we have to find the maximum, right? So if we know that the maximum value of 1 in the previous rows is this, so I have to find logically another another index in the next or the remaining rows which will be having an index or which will be having greater number of ones. So basically, if I'm pointing here currently, so if I'm moving to the next row, so this answer is stored, right? So in the next iterations, I have to find logically the new index, or I want a newer index which will be pointing to the left hand side. I hope you're getting what I'm trying to say, that we know, let us repeat that, we know that we have found this answer by pointing to this index, and this is the maximum answer or the maximum number of ones till now. But if I want to find another answer, then I will have to search in the next row in the left hand side only, because there is no point of searching again from this point, because we know that we have found the maximum value till now and we have to update our answer to get more number of ones. So therefore we will be starting from the last pointer of j only. So in this case, our last pointer of j was pointing here, so we will be start searching in the next row from this pointer. So the elements in this pointer in the next row will be are 0 0 1 1. So here we see that our last value of jth pointer in the previous row was this, and now I have to find the next bigger value of the total number of ones, or the less smaller value of j, because if the value of j is smaller, then our total number of ones will be greater, because we are using the formula of number of rows minus the column number, right? So if my this value is smaller, then my this complete value will be getting a bigger value, right? So basically we have to find a lesser column so that our this complete value can be having a bigger value. So this is the relation between the number of columns, the lesser value of number of columns, and the final answer. I hope you got this point. So after that, during the next iteration, we will be moving in the next row, right? So my previous pointer was here, and in the next pointer, and in the next iteration, I will be moving on to the second row. So I see that my this value is not 0. So there is my this value, my this value is not 1. So there is no point doing iterations in this row, because we see that we have already found an answer having value 3. But if I'm moving this, so I was moving in a hope that I will find another bigger answer or bigger number of ones or the lesser value of column. But as I moved to the next row, I saw that the previous index where I left in the previous row, and if I keep that particular pointer or the column pointer same, and I move to the next row, I find that the next row, by keeping the same pointer, is not having value 1. So there is no point doing computations, as it is logical that if keeping the previous pointer same in the next row, I'll not be getting the number of ones greater than the previous answer. So basically there is no point of doing iterations here. I hope you're getting this logic, because this is the main logic how we will doing traversals in the complete matrix. So I will move in the next row, keeping the column pointer same and incrementing the row pointer by 1. So the next row values are 1 1 1. So here in this row I can see that if I kept my previous pointer same as it is in the previous row, so I am getting a 1. That means if I'm getting a 1 here, that means that, or that sounds logical, that the previous value of column through which I got the maximum number of ones will now be updated, because we have found another value of column in some other row which is having a lesser value than the index when we found our first answer. So in this, the column index was here, and in the next row our column pointer was here. So basically this, as I discussed this relation, in this the column value is lesser than this one, so my final answer will be a greater one. So therefore I'll update my answer value to this, and I will move to the next row. One thing to note here is that as soon as I update my final answer, I will be also updating my, here I am updating the value of count of the total number of ones. After that, by doing this updation, I will simultaneously update my value of answer, that is the final answer I have to return the row number in the zero based indexing form. So I'll be moving again in the next row to find whether, or to check whether I can find still a lesser value of column, so that I can increase my final value of m minus column, that will be our answer, right? So I see that, yeah, again there is 0. If I keep the pointer same, then again there is 0. So there is no point doing further computations. So this was the complete approach of how we'll be doing it. So let us now discuss the time complexity of this approach. What is the time complexity of this approach? So we can see that we are not traversing each and every cell. Instead of what? Instead, what we are doing is that we are reducing the rows and columns we are searching. So if I started from this row, first of all, if I started from this point, then I started reducing my column until I get a zero. So in the worst case, we can we can traverse all the columns, right? That means m. And in the worst case also, we will traverse all the rows. So it will be plus n. So the time complexity becomes big O of m plus n, because instead of traveling or traversing each and every cell, we are only traversing the number of columns and number of rows. That is, in the worst, if this is my matrix, then in the worst case, I will be traversing till the zeroth column, and I'll be traversing till the nth column, nth row. So time complexity becomes big O of m plus n. Further, if I talk about the space complexity, the space complexity is logical that it will be big O of 1, because we are not again using any space. So I hope this approach is pretty much clear to you. And as I told you earlier that this same approach or this same logic of big O of n plus m time complexity was used in a question which was asked in Amazon, that is, find the element in a 2D sorted matrix. So you can go on to our practice channel and find that video again there, and you can again see that approach and another version of this question, how it can be asked. So now, after discussing all the three approaches, that is first of all the brute force approach, and after that we did something better by using binary search, and again we tried something better and more efficient by using the logic that, or the fact, or the stat that a row is sorted, and hence we can eliminate the number of rows and columns in each and every step. So let us now move to the coding part, where we will start implementing two approaches. The first approach will be the binary search approach, and the second approach will be the final approach. So let us now look how we'll do the coding. So this is the practice portal of Geeks for Geeks, where you can find many questions on different tags and categories, like on the difficulty level, on the company tag, on the topic tag. I'll be sharing you the problem statement link in the description below, so you can get to this page or this practice portal and submit your solutions here. So before starting, as we can see that this problem is a medium level problem, and being a medium level problem, its accuracy is less than 45%. That means this problem is pretty much complex, and to reduce the time complexity from n cross m to n log m, and to finally reach the time complexity of n plus m, is quite logical, and it uses a lot of your mind. So therefore, the accuracy of this is reduced to less than 45%, just because of the fact that we have to solve this in big O of n plus m time. So most of the candidates can logically reach to the n log m time, but when it comes to reducing that time complexity to from big O of n cross m to n log m, then finally arrive at n plus m, is a very tedious task, and it requires a lot of gray matter to arrive at that final solution. So that's why it is asked in most of the companies. So let us now start with the coding part of binary search. So first of all, we will be implementing the n log m, that is binary search approach. So as we discussed that in binary search, we have some few steps involved. So the first step is determining the low and high values. So before implementing binary search, we said that we will be iterating all the rows, and on each row we will be implementing binary search, having search space as total number of columns in each particular row. So my count will be storing the maximum number of ones, and an answer variable which will be initialized to -1, because it is asked in this question that if there is no row in which, if by doing the traversal in each and every row, if we find that there is no such row that is having any number of ones, then we have to return -1. That is, if no such rows exist, we have to return -1. So that's why we are initializing our answer as -1. Therefore, I use the count variable to store the count of the maximum ones till now, and answer which will be returning are final value of row number in the zero based form. So we will be start traversing each and every row. So, and for each row, I'll be finding the index of the first one, right? So I'll be using a solve function, which in which I'll be implementing the binary search. So in this binary search, I have to pass an array, 2D array, the row number and the value of columns, total number of columns. And if my if after implementing the binary search for that particular row and having search space equal to total number of columns, if there is no one found, then I'll be returning -1, depicting that there is no one found, right? So if my value of index is equal to -1, or we have to find the answer, right? So if I say that my value of index is not equal to -1, that is we have found some value of index that is having depicting that, yeah, we are getting encountering a 1 in that particular row at some particular column, then we will update our answer. That is why I use the formula of number of columns minus the index at which I am getting the first one, and if it is greater than my count value, the count value depicting that maximum number of ones encountered so far. So initially it is 0, and if I found in the first row any index having 1, so basically, so logically it will be greater than the count, that is 0 in the first iteration. So I'll be updating my answer to I, because that is, this is the row, or it can be the possible answer, so it will be a temporary answer stored, and I'll update my value of count or total number of ones as index as m minus index. So after this, when all these row will be traversed, I'll be normally returning my answer. So now it's time to implement the binary search function. So our binary search function will be returning an integer value. Integer value means that I have to return an index here. So I have to pass the 2D array. In this question, 2D array has been passed as a 2D vector. So sorry guys for some technical issues, but I hope that my screen is visible now. So can you please acknowledge again that whether my screen is visible now or not? Please acknowledge so that I can move further with this live session. Okay, thank you. So now I'll repeat the part which was missed due to the technical issues. So what I said was that I was describing this code how you will visualize it. So basically, by implementing binary search, we just the steps are to just check the first of all the mid value and to check whether this mid value can be a possible answer or not. So general in the general binary search, as we discussed that once we find the value to the target value, or we find that the mid value is equal to target value, we normally return it. But in this case, what we have to do is that we have to find the lowermost value of index, right? So if I encounter a value equal to 1, then that can be a possible answer, that's right, but we can still do it much better and we can find the minimum value of index. So there is still room or chances that in the quest of finding a minimum index, then the current value, we can move to the left hand side, right? So we will store this value because it can be the possible answer. So we will store this value of mid in the temporary temp as the possible answer in the answer variable, and we will be moving to the left hand side of the search space. So high will be updated to mid minus 1. By doing this updation, we are moving to the left hand side, right? So else the else part says that if my this condition is not satisfied, that means that the value of mid is not equal to 1, right? That means the value of mid, if it's not equal to 1, that definitely it means that because it will be 0 because it is a binary 2D array or a boolean 2D array. So the row is sorted, and hence if I am not finding the value equal to 1 in the mid, then I have to move in the right hand side part because the array is sorted. So after 0 there will be definitely, if there is 1, so we can find 1 after on the right side of the current value of mid. So therefore we will be moving in the right hand side. So to move in the right hand side part or in the right side of the search space, we write this condition, that is low is equal to mid plus 1. So I will write this here again, that is else low is equal to mid plus 1. So this is all about this binary search or this main function, which is the main life of our binary search function. And finally, when we'll be doing all the iterations, then we will normally return the answer. The answer it will be returning is the index. Okay. So here we will initialize our answer to -1 because we talked about this earlier, that in case if we are not finding any 1, then we have to return -1, right? -1 depicting that there is no 1 found in that particular row with these m columns, right? So yeah, if it returns -1, so this condition will be false and till there will be nothing updated. So this is all about this binary search. Let us try to submit this approach. So yeah, there is no any semantic or syntax error. So yeah, let us try to submit this approach. So we can see that we have perfectly executed this approach, as the time complexity of this approach is n log m. And if we talk about the constraints here, the constraint says that the maximum value of n and m can go to 10 raised to the power 3, right? So if I talk about the time complexity and how it will look, so we said that the time complexity of this approach was big O of n log base 2 of m, right? So if I take the maximum value and find the time complexity which will be taken in the worst case. So if n is 10 raised to the power 3 and m is also 10 raised to the power 3, so time complexity will become 10 raised to the power 3 log base 2 10 raised to the power 3. So if I solve it, I'll get 10 raised to the power 3 into 3 log base 2 10 will give me around 3. So if I take the CEL value, so it will be finally 12 into 10 raised to the power 3. So yeah, we can pretty much implement this because the maximum time or the maximum number of computations we can do in 1 second is 10 raised to the power 9, and it is way much, and this the final time which in which we are implementing this n log m binary search approach is too much way lesser than 10 raised to the power 9. So it is therefore perfectly executed, and this is the proof why it is getting executed. So it is a mathematical proof. So now if we move down to the next or the final efficient approach, then let me first erase this. So I hope this binary search code is pretty much clear because we discussed this binary search approach, we coded this binary search approach, and while coding I just discussed you the logical and made you visualize how this binary search is working. So I hope I did pretty much well to make you understand this approach. Now we'll be discussing the last and the best efficient approach, that is approach of big O of n plus m. So now, as we said that before starting this approach, we will be starting from the rightmost. We'll be starting from the top rightmost corner, right? So for that condition, our top rightmost corner will have value of row as 0 and value of column will be m minus 1. That is the last index, right? So, and again, I'll have to keep a variable answer so that I can return an index, right? So if we are initializing it -1, again I'll repeat that why we are initializing it -1, because in the case if we didn't find any row having any number of ones, right? Suppose if we are having n rows and by traversing all the n rows we didn't find any row such that we find a single one in any of the rows, so we will have to return -1 depicting that we did know there is no such row having any particular value of or having any single value of 1, right? So yeah, therefore we are initializing it to -1, and if there is no rows having value of 1, having 1 as a cell value, then we will return -1 as it is asked. So yeah, we'll now move on to the implementation of that. So now in this condition, we'll be writing that up till how much iterations I have to perform, right? So in the worst case, my column value can move to m columns. That is, if I'm starting from the last index, so the worst in the worst case, I can reach to till the 0th index, right? If I move to the left hand side, and my row can in the worst case can be to the last row, right? So if I'm considering 0 based indexing, so row, the last value of row will be n-1, therefore right, this is the condition. So if I depict you in this, I'll repeat it for you again, that if this is my matrix and this is my m columns and this is my n rows, so in the worst case if I'm starting from this, in the worst case I can reach till 0th column if I keep moving on the left hand side in the quest of getting 1 again and again, and to find all the possible values of indexes, or in the quest of moving that if I can still find maximum number of ones in the any further or in the following rows, so I will in the worst case I will be traversing all the rows, right? So if I say I points to my row pointer and j points to my column pointer, so j in the worst case can be greater than equal to 0 and I in the worst case can be less than equal to n-1, or we can say that I is equal to I less than n, right? So this is what I'm trying to do in the iteration part. So yeah, this is my condition for all the traversal or all the iterations. So now, as we discussed that we will check if my current value of this is equal to 1 or not. If it's equal to 1, then we can still find some other better or the lower value of index. So I will decrement my column value by 1, and I will update my answer value to row. So basically what it does that if we find 1, then we can still move on to the left hand side to find another one, keeping that row same. So my answer will be updated to row, because if I'm finding a 1, then if I'm moving to the left hand part, so as if I'm moving again, if I'm moving to left hand side in a particular row, that means I'm increasing the count of the total number of ones, because as we said that we are using this formula, right? So if this column value is getting decreased every time, this complete value will be getting increased. This is the relation between column and this complete value. So that's why if I'm moving on the left hand side, my number of values of ones will be increased. So therefore I'll update my answer to this as the current row, right? So this is what the logic I'll be using here, right? And yeah, so else, in the else part, if I'm not finding one, then I'll be moving to the next row as we discussed. And after all these iterations, I will normally return my value of answer. So let us now review this code. Okay, just compile it and run to check whether there are any errors or not. Yeah, so there are no errors. It is running successfully. Now we will submit it. So as we can see that we are getting it accepted. So we can see that we are getting it accepted, and the time complexity, I'll repeat it again, that it is big O of n plus n, big O of n plus m, and space complexity is big O of 1. So I hope you guys liked this video, understood all the 3 approaches I tried to explain. And if you want to solve another question with the same logic, the problem statement name is finding the element in a sorted 2D matrix. I have already made a video on that, so you can go out on the practice channel and see that video. If in case you have still any doubts, you can comment it down on the comment section. I'll surely look into it and try to answer as soon as possible. So furthermore, these type of questions are having medium difficulty, but their accuracy is still less than 45%, just due to the fact that most of the candidates can, almost 80% of the candidates can reach out from m cross n to n log m, but the harder part or the topmost peak is to reaching the big O of n plus m solution. So this is what the interview mostly asks, and by expecting this solution, they wanted to check your logical ability, that how you can traverse matrix and how you can use the stats that you are having, that is the or observation that whether row is sorted or not. So this is what all the 3 approaches. We started from the brute force approach, and just to mention that the way we are approaching the problem statement, starting from brute force to the best optimal approach, this is the same manner in which you have to answer the interviewers, that we start from the brute force approach, we just step by step enrich our algorithms, and we move over to the finally the efficient approach. So this is the way to implement. So we implemented all the approaches we discussed, and while implementing the coding part, we hand to hand discuss, and we simultaneously discuss what we are doing in the coding part, just so that for the sake that we can visualize what we are actually doing, because visualization is most important part while writing the coding part. So yeah, this is all about this today's session. My name is Dhananjay Mishra, and stay tuned for more such informative live sessions here on where we'll be discussing about the recently asked interview questions and discussing how to approach the problem statement from brute force to the optimal approach. Thank you for watching, guys. Happy coding.